Hello, welcome to Anson Griffin's occasional series in Matlab tutorials. Today it is indeed Matlab, as I said, and we are looking at motion estimation and subsequently motion compensation for a predicted frame. So I've done the thing in Matlab and I've published my report. So I'm just looking at I've done my table of contents here. So we're going to do full PEL or integer PEL search, and then in number just after number 8 we're going to do half pixel, and for half pixel, as you are aware, you'll get a more accurate estimation. And as you see in number 12, you'll see that integer PEL will be much quicker than half PEL, but half PEL will give a higher PSNR. That would be in step 8 there. Okay, so hopefully that's okay. We just have the code here. I might just blow this up a little bit more. So we have it there. We've closed all, cleared the screen, cleared all variables. Now just slow down here. So we file open and we did file read, and so I have the two frames read in. We have the anchor frame and we have the target frame. And there's a function that's provided, EBMA, estimated block motion algorithm. I just scroll a little right so that we can see there. So we can specify there's 4 inputs, 5 inputs, the block size, the P, that's the radius or the search areas, and the accuracy. So we did tick tock, that'll get the recorder time, and the recorder time for just is 6.61 seconds. So just to explain or show a bit more, so what we have there is we have the anchor frame and we have the target frame, and we're searching. Remember, as in the lecture, we do we're trying to provide the motion vectors. Now just the motion vectors for each 16 by 16 block on the right here in the target frame. The building is static, and you can see here that the only thing that's moving is the foreman's head, and you can see even these are successive frames, and the foreman has moved his head quite rapidly, so that here on the left he's more or less fade on, and on the right he's looking well towards his left or right. So we got the motion vectors from that function above, and we used the quiver command, and there we have the motion vectors overlaid on the original. Now what's the motion vectors telling us? Well, obviously in the background here for the building, that hasn't moved, so the motion vectors are going to be 0. And then you can see here that around the foreman and the foreman's face, the foreman's helmet and head, you can see that he's doing a fairly quick turn. So most of the motion vectors are going from northwest to a southeast direction. I hope you can see the mouse there. So now obviously there are some not going that way, but by and large most of them are going in a northwest to southeast direction, as we'd expect. Now I displayed the predictor frame. This would be what the decoder would work out. And if we just go down here, and there's the decoded frame. Now I know most of our students will be looking at this on YouTube, but you can see there's a fair amount of error, especially around the face there, just around his nose and his eyes. But we're just saying that's what happens. So, and then the building is fairly spot on. Why? Because, well, the motion vectors are 0 or as close to 0. This makes no difference. Now, what I next did was I had the actual frame, and then that would be at the encoder end, and then I did the decoder frame, which is that just there, and I subtracted them. And if they were identical, or the more identical they are, the blacker the difference frame would be. So where there's black, there's where I'm moving it over here, where there's black, there's no change, and then obviously white, the whiter it is, the greater the change, the greater the error. Now you may say to yourself, why is this helmet black if that was moving so quickly? But remember, it was uniform white, so really, even though the blocks may be moved all around, you're still ending up subtracting more or less pure white from pure white. Okay, and most of the white there is around his face, just there, around there. So when we did, this is as we'd expect, because when we did the predicted frame, we got a fair amount of error. Peak signal to noise ratio for that one is 27.49, fairly poor. Then we did half pixel estimated block motion estimation. So instead of getting integer pel accuracy, we're now getting half pel accuracy. So we're getting more accuracy. So how did I do that? I resized the target frame to be 2. I used bilinear interpolation, as I explained in class, and using this function that's provided, EBMA, I've set the accuracy equals to 2, so I'm more or less telling it the half pixel accuracy. Call it again. Sorry about that. Just to see all of that out there. And the search time here is 24, which is kind of right, because remember the previous one was 6, so we've doubled it in the x, you've doubled in the y, so that's 2 by 2 is 4, so you more or less get 4 times, so that's the answer there is quite believable. So we have 24 seconds and 6 seconds, which is about pretty much spot on. I'm now going to display the motion vectors with the half pixel EBMA, same as before. Let's display the predicted frame and the error frame. There we have it. There's the predicted frame. We've still got some fairly big error around the center of the face. And that's it. Now what would be left to the student, just very simply, is to get the PSNR for the half pel. The function is there in step 8, and we would expect that the half pel PSNR would be higher than the integer pel. Okay, so hope that helps. Thanks for listening. Bye.